Good morning, everybody. Today we're going to continue talking about magnetic forces. And in particular, we're going to talk about applications of magnetic forces. There really are a lot of applications of magnetic forces, and we're not going to be able to talk about all of them, but we'll pick a few and go into them in a little bit of detail, so you can get a sense of how broad the implications of magnetic forces are. Before we do that, let's just review where we're coming from here. So last time we talked about magnetic force on a moving charge, because moving charges are the only thing that experience magnetic forces. And on a wire containing a wire that has a current running through it, where there are a lot of moving charges in the wire. So let's just remind ourselves what we know. So force on a moving charge if we have some charged particle here traveling with some velocity v, and there is a magnetic field in the region due to something in the surroundings, the applied field, then the force on the moving charge is given by a very simple equation, QV cross B, which is another of these things that you have to memorize, one of the four things you have to memorize. And we see from the fact that there's a cross product in this equation that there are two important points to note. One is that the magnetic force is perpendicular to the particle's velocity, and it's also perpendicular to the magnetic field. So again, we have the mathematical formalism of the cross product represents this idea that if V and B define a plane, then the magnetic force on the moving particle is going to be perpendicular to that plane. And we find this with the direction with the right-hand rule. So in this case, if we have velocity in the plus x direction, and so we point our fingers in the plus x direction, we want to fold our fingers toward the plus y direction, where there's a B, and our thumb sticks out in the plus z direction. So in this case, the magnetic force would be plus z, which is out of the page in this case. We also found the force on a piece of current-carrying wire just by adding up the forces on every moving charge in the wire. Not a big surprise. So current-carrying wire of length delta L. And here the magnetic force on the moving charges is equal to I delta L cross B, where delta L is in direction of conventional current. And of course, we have to note in this case that pay attention to the sign of the moving charge, because if it's negative, then the force will actually be in the opposite direction to the direction of V cross B. In the case of a current carrying wire, it turns out that that we get the same answer assuming conventional current as we do using electron current, because the electrons would be moving the other way. And so we're going to get the right answer either way for direction. So what are we going to apply this to? And this is, by the way, not an equation that you have to memorize. That will be given on equation sheets. But do memorize the force on a single moving charge, because it's hard to derive backwards from this. So we're going to talk about several different implications and applications of magnetic force. The first thing we want to talk about is motional EMF, which explains basically how a generator works. We are going to talk about, and in talking about motional EMF, we'll have to think both about microscopic issues like what's the force on one moving charge in a wire, and then we're also an object, and then we're going to have to think about more macroscopic issues like what's the force on the whole wire. We're going to talk. I'd like to talk briefly about another microscopic thing called the Hall effect, which is actually something that lets us actually determine the sign, experimentally, the sign of moving charges in a conductor. And then I want to talk about viewing this whole phenomenon from a moving reference frame. One of the things that actually led Einstein to create the special theory of relativity. So, and we may or may not get to magnetic torque, which actually is important, and it has to do with torque on a compass, but you can read that in the book. So, motional EMF. So we have just a neutral copper bar. It's not connected to anything. And we're moving this copper bar horizontally, looks like in the -x direction at some constant speed v, through a region where there's a magnetic field out of the page in the +z direction. Is there a reason this bar would polarize? And if so, how might it polarize? So is there any reason at all, there's no electric fields here, but is there any reason at all that this bar might polarize? So just think about this for just a minute. So let's think about what might be going on inside this bar. So let's draw over here a picture of the bar. And let's think about the particles inside the bar. Now, there's obviously two things inside the bar. There's these, this is a metal, right? So we've got these, so every atom has given up an electron contributing to the mobile electron C. And so we have these positive atomic cores, ions, that are bound together, of course, by covalent bonds. And then we've also got a bunch of mobile electrons. And of course, both things all through the bar, but it's going to be cleaner if I don't draw them all. Now let's consider a mobile electron. So the mobile electrons are inside the bar, and since the whole bar is moving to the left at speed v, then this electron is also moving to the left at speed v. We're moving at a constant speed here. So we're going to consider the system of one electron. And so now we have an electron moving to the left in a region where there's a magnetic field out of the page. So think for a minute about the magnetic force on that mobile electron. So we have V cross B is in the plus Y direction, but it's an electron. So therefore we have to flip the sign of the force. So what we're going to get is actually a downward magnetic force on these electrons. Now, is there a magnetic force on the positive atomic cores? Well, let's see. They're moving to the left at speed v, so v cross b is up. So there would indeed be a magnetic force on these things, but they can't move. They're rigid, they're pretty rigidly held in place in the bar. The mobile electrons, on the other hand, are totally free to move. So this force on the mobile electrons is going to lead them to move down and start to accumulate on the bottom of the bar. And this means that if the entire mobile electron sea in the bar shifts down, that we're going to be left with a deficiency of negative charge at the top of the bar. So we've actually got, we're going to end up with the bottom of the bar being negative and the top of the bar being positive, just because we're moving this neutral copper bar through the magnetic field. Well, that's kind of interesting. What would happen if we move the bar the other way? So think about what's going to happen in this situation, and then get ready to answer a question about it. So the question is going to be, what happens? And we've got three alternatives here. One is the bar polarizes like this. Two is the bar polarizes like that. Three is some other polarization. And four, I lied there, four alternatives, is nothing happens. So the bar doesn't polarize at all. Okay, so let's see what you think is going to happen here. So those are our alternatives. So we have a majority vote for answer 2. So negative on top, positive on the bottom, the opposite of what we saw when the bar moved to the left. So let's check that and make sure it's right. So we'll consider an electron here inside the bar. it's moving, the bar is moving to the right here with speed v. And so we have v cross b is down, but this is an electron, so we're going to get a magnetic force up. And so mobile electrons will move up to the top of the bar, leaving a deficiency of positive charge on the bottom of the bar. And so, in fact, answer 2 is indeed correct. Now, there is a force on the positive atomic cores, but they can't move. So that's how we get this polarization. So in the first case, we got positive on top, negative on the bottom. In this case, we got negative on top, positive on the bottom. Well, it's kind of interesting because it looks like we just made a battery. So what's its EMF? The EMF of this battery, so here's our battery. So the EMF is going to be equal to the potential difference across this battery, measured from the difference from the top to the bottom of the battery. So if we can figure out what the potential difference is there, then we could figure out what the EMF of the battery is. So EMF equals potential difference across the battery. I guess I'll put battery in quotes. It's a different kind of a battery. So what we need, of course, is we need to know what the electric field inside this, to get delta V, we need to know what the what this electric field inside this bar is due to the polarization, okay? Because these charges on the top and the bottom are going to make an electric field, and so that electric field due to that polarization, if we knew that and we knew the length of the bar, which is presumably L, then we could calculate delta V is going to be equal to the electric field times the length of the. Yeah, I think it's not. We'll talk about, is this the principle used for those shaking charging flashlights? And it's actually the principles used to make a generator where you turn a crank. It kind of depends on what's moving when you shake the flashlight, and we'll come back to that because it's an interesting thing. So we can find the EMF of the battery if we could calculate, we knew the electric field inside here. So let's think about, let's say what we know. So we know the speed at which we're dragging the bar. It's a constant. We know the magnitude of the magnetic field. We know the length of the bar. So how do we calculate, how do we figure out what the electric field inside the bar is? Well, it helps to think about how we got to this polarization and why it's polarized this much and not some other amount. So initially, when we're just starting out, so at time 1, here's our mobile electron. It's moving that way. The magnetic field is out of the page. And so we get this magnetic force on the electron. And because there's no force opposing that, that's the only force acting on this electron. The electrons all sort of move up toward, shift up toward the top of the bar. So at time 2, a nanosecond or so later, now we've got some charge on the top of the bar and therefore some positive charge on the bottom of the bar. And now if we consider electron here, it's moving to the right at speed v, and there's still the same magnet, so there's still the same magnetic force. But now there's actually a small electric field in the bar. It's not as big as it's going to be, but there's a little bit of an electric field, and so we're going to get a small electric force opposing this magnetic force. Well, you can see what's going to happen. This keeps going until at some later time, we have enough charge built up here on this bar that now there's a big enough electric field inside the bar that the magnetic force on the electron is actually balanced completely, exactly equal and opposite to the electric force. So the electric force is equal in magnitude to the magnetic force. So F net vertical equals 0. So we reach this final polarization. So this is steady state polarization. Well, maybe we can use this to figure out the magnitude of the electric field. So we know that in the steady state, the magnitude of the electric force is equal to the magnitude of the magnetic force. So we have QE, where E is this electric field we really want to know. So here's our unknown. The electric force on the electron is equal to QVB sine of 90 degrees here. And so in this case, we actually end up with the electric field is equal to the speed times the magnitude of the magnetic field. Now, this is not some general equation. Okay, this is just something we've derived in this particular situation. So this is in this specific situation. But now that we know the electric field, because remember we knew the speed and we knew the magnitude of the magnetic field, we can actually find the potential difference across the bar. So it's this potential difference that we're interested in between the top of the bar and the bottom of the bar. And that's just going to be equal to E times L, and we're talking about absolute values here. And so that's going to be equal to VBL. And so that is the EMF of our battery. So can this be useful? Can this battery do something? Well, sure. So let's consider a situation where we try to put it into a circuit. Now, sliding a moving a bar to the right at constant speed is not necessarily going to be all that easy. So we're going to eventually want to think of some other geometry. But let's consider just a simple situation in which you are dragging this bar to the right at constant speed. So here's our bar. There's a magnetic field out of the page. It's moving to the right at constant speed, bars of length L. But now what you've done is you've put the bar on conducting rails, big pieces of metal that are conductors. And you've hooked up a resistor to it, a light bulb, say. And so presumably we could light the light bulb by doing this. So let's think about, and by the way, we're sliding it along conducting rails. We're at very low friction. But that's okay, because you're pulling on it to slide it, so you're going to make up for any frictional losses. So in this case, which direction would conventional current flow? Clockwise, counterclockwise, or there wouldn't be any current in this situation? So we have a majority vote for clockwise. Almost everyone thinks there will be current. So let us check this and see if the majority is correct. So you've picked clockwise. So let's check. Here's our bar. Here is our mobile electron, which is the thing that can move. So that's what we care about, moving that way at speed v. We have a magnetic field out of the page. So V cross B is down. This is an electron, so that means the magnetic force is up. So we get electrons on the top, excess electrons. We have a deficiency of electrons on the bottom. So let's add that to our diagram here. Okay. So now we have to think, in our minds, we replace this with a battery with the positive end down and the negative end up. And so we know that conventional current is going to flow from the positive terminal of the battery to the negative terminal of the battery. So presumably we will have conventional current flowing like that. Yeah, okay, so wouldn't F be down? It would if there was a positive charge, but this is but as Alex says, yeah, this is an electron, so you have to actually remember to take into account the negative sign of the electron in this F equals QV cross B, right? And that means the light bulb, so we've got this conventional current flowing clockwise, and that means the light bulb will light, which is kind of interesting. So this looks exactly like an electric circuit powered by a battery, except actually we've got this motional EMF polarizing the bar and acting like a battery. Now, let's think about energy and power in this situation. So we're lighting the light bulb, and that must mean that energy is being dissipated in the light bulb. It's going into thermal energy of the bulb filament, which is getting hot, and it's giving off photons in the visible and the infrared. And so there has to be some energy input into this circuit somewhere. So where does the energy input come from? Well, the question really is, this bar is moving to the right at constant speed under negligible friction. So in principle, so the net force on the bar has to be zero. But is it actually going to glide along forever without us pulling on it, or do we need to pull on the bar? So let's actually think about the situation that we've got here. So let's redraw our circuit, I think. Yeah, let's redraw our circuit. So here's our moving bar. Here's the conducting rails. Here's our resistor. And you correctly decided that conventional current was flowing clockwise around the circuit, which also means that conventional current actually has to be flowing this way through the bar against the electric field. And that's right. I mean, so we've got negative charge here, we've got positive charge here. And so the electric field due to these charges is clearly here. And so conventional current is actually flowing the wrong way through the battery. And that, of course, happens in any battery, right? That's why this non-Coulomb force is required to keep the battery polarized. And in this case, what's the non-Coulomb force? It's a magnetic force. It's absolutely not an electric force. That's what keeps the battery polarized. Either the bar is just going to coast along forever, or there's going to be some force slowing the bar down. Is there a force? The bar down. Answer is there actually is a force slowing the bar down. And we can figure this out by now we're going to switch systems. Before we just had the system of one electron, now we're going to consider the system, the entire bar, and ask if there's a magnetic force on this bar, because this bar is a current carrying bar. So here's our bar. We have conventional current going down. We have a magnetic field out of the page. And so now we get to use our other equation for magnetic force. So the force on bar is going to be the conventional current times the length of the bar times the magnetic field times sine of 90 degrees. And so there is a magnetic force on this current carrying bar because we've got a current in a magnetic field. And let's think about the direction. So it's the direction is going to be delta L cross B. So delta L is in the minus Y direction, B is in the plus Z direction. So actually this magnetic force on the bar points to the left. So we'll add this to our diagram here, which is getting very busy, but we've got this magnetic force now on the bar. And that means that to keep the bar going and keep this going, we need to exert an equal and opposite force forced by us to keep the bar going at constant speed. So the energy input comes from whatever force we're using we must exert a force to keep the bar moving. So we're doing work. So we could actually calculate the power. Power input is what is the work we do per unit time. Yeah, the laws of thermodynamics always do win. No perpetual motions here, machines here. I'm not sure the world would be better if we had perpetual motion machines, though. You can think through some interesting applications. So this is the force by U, delta x over time delta t. So this is the work you do, the force you exert per unit time. And so this is going to be equal to, we know how big the force you exert is. This is just the conventional current times the length of the bar times the magnetic field. And then it's times the distance you move in some particular time. But this, of course, is actually just the speed of the bar. So this is v, it's dx dt. So it looks like this is I, L, B times v of the bar. So what have we done here? Well, this is called motional EMF because it's moving an object, a conductor, through a magnetic field that generates a polarization, which can then be used to drive a current. An interesting way to do this backwards. So consider a different situation. No, it's not emotional EMF. We like to think there are no emotions in physics. So let's consider a different situation where we have a bar here on these conducting rails, but instead of a resistor, we actually stick in here a battery. And there's still a magnetic field out of the page. So let's see what's going to happen in this situation. We're going to get our clockwise conventional current. Actually, I think I want the battery to go the other way. Given, let's make the battery go the other way. So we're going to get here a counterclockwise conventional current. And now that we have a conventional current running up through the bar, there's going to be a magnetic force on the bar. So we're going to have force on bar. It's going to be I delta L of the bar cross B. So it's going to be I delta L is up, B is out of the page. So in this case, we're driving a current now. So the key difference here is that we've actually put a battery here, not a resistor. So we're driving a current with a battery. We actually have a force on the bar to the right, and it starts to move to the right. And as long as we keep driving the current, there's this force, and it accelerates and goes faster and faster. And we've actually made a rail gun, because this thing can be shot off this bar at high speed. Yes, I thought you'd be happy about that. I'd like to tell you briefly about another effect that we can understand at the microscopic level called the Hall effect. It's another example of magnetic polarization. So magnetic polarization again. And the Hall effect is actually important because in a fundamental way, it lets us decide whether the mobile charges in a particular material are positive or negative. So we can distinguish in another way, technologically, because the Hall effect can be used to measure magnetic fields. So the magnetic field sensor in your phone, for example, is actually consists of these little Hall effect probes. So the basic idea is that this comes from the fact that the magnetic force on positive and negative charges is in the opposite direction, right? So here's a picture of the circuit we want to talk about. So here's the positive pole. So we have a battery connected to a bar of some new material, and we want to figure out whether they're positive or whether the carriers in this new material are positive or negative. Now, I think I mentioned, although we didn't talk about it a lot, that there are materials that do have, in fact, positive mobile charges. Many semiconductors do. They behave rather differently from metals. These positive mobile charges in this case are called holes. And you can think of them as, instead of an electron moving through the lattice, it's a place where there aren't any electrons moving through the lattice. So it's almost like a bubble with nothing in it moving through the lattice. And mathematically, it turns out these behave exactly as if there were real particles with mass. And so many semiconductors actually have holes as the thing that moves rather than electrons. So, so we want to know which this is. And so what we've got here is a circuit that the battery is connected to our bar of this new material, and we also have a little magnet here to apply a magnetic field. So we know which way conventional current is going to go in this circuit. So we know that, and we know that the electric field in particular driving the current here and I'm going to call this electric field for the circuit, is going to be going down in the bar. And so mobile electrons, if they are electrons, would actually move So we have this field down. And so if the movable charges are negative, they would actually move up. And if the mobile charges are positive, they would move down in the bar. So, so minus charges would move up and plus charges would move down. Now let's just consider the two cases and see what happens. So let's see what happens if we're going to put this magnet here. So we've now got a magnetic field from this magnet that is in the x direction, and the electric field inside the bar that's driving the current is in the negative y direction, okay? So let's see what would happen if our mobile charge is negative. So if mobile charges are negative, we'd have an electron here moving in the plus y direction. And so would there be a force on this mobile electron? So V is in the plus y direction, B is in the plus x direction. And so I get a force, a magnetic, V cross B is into the bar, sorry. But because this is an electron, the magnetic force is actually out of the bar. And so we'd actually end up with electrons piling up here on the front surface of this bar. Okay, so the front of this bar would be negative and the back of the bar here would be positive. So that's how the bar would polarize. So let's see what's going to happen if this thing is if the mobile charges are positive. So if mobile charges are positive, we've got the electric field down, we've got a positive charge moving down. We still have this magnetic field in the plus x direction. So let's think about the force on a moving positive charge. V is down, B is in the plus x direction, my thumb sticks out in the plus z direction. So F magnetic is in the plus z direction. And so what we're going to get is positive charge building up on the front of the bar here, and negative charge building up on the back of the bar. So that in both cases, the force was actually in the plus z direction. And why is that? Well, because in addition to the sign of the carriers being different, the velocity was in a different direction. So now this is actually something that we can distinguish. So if we hook up a voltmeter very carefully so we put a voltmeter here and measure the potential difference from the front of the bar to the back of the bar. And the reason we have to be extremely careful is we really have to line up these leads really precisely, because we don't want to measure this component of electric field that's that's driving the current, which is very large. We want to measure what's really a very tiny polarization. But if we do this, in one case, we're going to get a positive reading. In the other case, we're going to get a negative reading. And so we can actually tell, whether the carriers are positive or negative. And you can use this backwards to measure a magnetic field, because if you know the sign of the carriers, then, and you know the amount of current you're running through this thing, then you can actually measure the magnetic field. And if you read about it in the book, you'll see how to do it quantitatively. Okay, perfect. So what I would like to talk about now is what happens if we look at magnetic forces in a different, from a moving reference frame. So magnetic forces in different reference frames. Okay. So what we're going to consider here is, and we're going to need help from two observers who are typically called Alice and Bob. And we're also going to need help from Albert Einstein to think this through. So we're going to consider a really simple situation. We've just got two protons. Which are moving to the right with some speed v. And at the instant we start out, they're some distance r apart. And so let's call these protons 1 and 2. What we're going to do is just figure out the total force that proton 1 exerts on proton 2. Okay? So, so there's going to be an electric force and a magnetic force. So we want net force on 2 by 1. So proton 1 makes an electric field down at the location of proton 2. And the electric force is just Q2E1, right? So that's going to be an E times a 1 over 4 pi epsilon 0 E over r squared. And that's going to be in the minus y direction. So we can draw that force here. So here's our electric force. Now, is there also a magnetic force on proton 2? Well, there ought to be, shouldn't there? Because proton 1 is moving. So presumably, proton 1 makes a magnetic field at the location of proton 2. Okay? So let's see. First of all, what's the direction of that magnetic field? So we have, this is going to be our hat. So the magnetic field at the location of, so B1 at the location of proton 2 is just going to be mu 0 over 4 pi E V V cross R hat over R squared, right? And so V cross R hat, that should be a magnetic field into the page. So we've got magnetic field into the page. And so the magnetic force on proton 2 is going to be E V cross B1. And so V is in the plus X direction, B1 is in the minus Z direction. So there's going to be a magnetic force up. And so we'll draw that. And we can calculate this because this is just going to be the magnitude. So the magnitude of the magnetic force is just going to be EV B1 sine of 90 degrees, which is going to be, and this is B1, the magnitude of B1 we get from the expression above. There's another sine of 90 degrees in there. So we're going to get a mu 0 over 4 pi E squared V squared over R squared in the direction 0, 1, 0. So which force is bigger? Well, so the magnetic force divided by the electric force is equal to mu 0 over 4 pi E squared V squared over R squared divided by 1 over 4 pi epsilon 0 E squared over R squared, which gives us a V squared up here and a 1 over 4 pi epsilon 0 divided by mu 0 over 4 pi here. And that gives us a V squared divided by 9 times 10 to the 9 over 1 times 10 to the negative 7. So that's V squared over 9 times 10 to the 16th. And that's actually a pretty interesting number because that is V squared over the speed of light squared. Now, where did the speed of light get in here? That's actually fairly interesting. So the magnetic force is going to be smaller, but as the speed approaches the speed of light, then the magnetic force can approach the electric force in this situation. Now, if we work this out for proton 1 on top, we find, of course, that the electric force on proton 1 is they repel each other, and proton 2 makes a magnetic field out of the page here. So V cross B, I'm sorry, out of the page as I draw it. So out of the page. So V cross B, so the magnetic forces are attractive, but the electric forces are repulsive. So that means that the protons are still they're gonna move apart. So the path of proton 1 is going to go kind of like that, and the path of proton 2 is going to go kind of like that until one of them, they hit the floor and the ceiling, right? And so if we want to do an experiment to see if this really happens, we have to employ an observer. So we'll employ Bob. So Bob sits still. He sees this. However, we have another observer named Alice, and Bob sees that, and what he sees is related to the fact that we had this electric force up, we had a magnetic force down, and so the net force was up, but it was a little smaller than the electric force. Okay. On the other hand, Alice, who's feeling very energetic, runs along with the protons. So she's moving at speed v. So what does she see? Well, what she sees is that there's a big electric force. But in Alice's reference frame, there are no magnetic fields because she's in her reference frame, the charges aren't moving relative to her. I mean, they're not moving horizontally relative to her. They're moving apart, but so that these magnetic fields at the location of the other charge are actually zero. There are no magnetic fields. So she sees a bigger force. Okay, fine. So they have watches, and they decide who's right by timing how long it takes these protons to hit the floor and the ceiling. So Alice measures time until protons hit floor and ceiling. And she gets 15 nanoseconds. And Bob measures time the floor and the ceiling, and he gets 20 nanoseconds because the force was smaller in his reference frame, so they weren't going as fast. Well, that can't be right, can it? Don't things have to work the same way? I mean, either it takes 20 nanoseconds to hit the floor and the ceiling, or it takes 15 nanoseconds to hit the floor and the ceiling. It can't take both, can it? So Albert Einstein's famous paper in 1905 was actually entitled On the Electrodynamics of Moving Bodies. And it was this paradox that he was trying to resolve. And what this led Einstein to see was, or to be able to show conclusively, was that time is running slower in the moving reference frame. So time runs slower for Alice moving reference frame than for Bob. So the laws of physics are the same. The forces are the same. Their effect on motion is the same. It's just that the time is running differently. So if Bob looks at Alice's watch as she runs by, he's going to say her watch is running more slowly than mine. Because in fact, for her, time is running slowly. You may have read science fiction books about the twin paradox, where identical twins start on Earth, but one gets in a spaceship and travels very, very fast out to some distant stars, and then travels very, very fast back to Earth. And when the second twin gets back to Earth, they're actually younger than the twin who stayed on Earth. So this is known as the twin paradox, except it's not a paradox. It's actually what would really happen. Time moves much more slowly in the moving reference frame. And so for the twin who was traveling at very high speed, time moved more slowly, and that twin actually aged less. This is indeed special relativity. This is the theory of special relativity. Yes, the faster you move, the younger you're going to be. Now, there's actually an example of this, which will turn out to be something we're going to want to talk about later. Cosmic rays, which are usually high energy protons coming from outside the solar system, actually, and they hit the top of our atmosphere and go through nuclear reactions. And one of the things they produce is muons, which are leptons like electrons, but they're just heavier. They're not subject to the strong force, so they don't interact with air molecules. They don't interact with nuclei. And they travel down through the atmosphere and reach the Earth, and we can detect them. The problem is that muons really only have a lifetime of 2 microseconds. So they don't last more than 2 microseconds before they fall apart. And it takes, but it would take 20 milliseconds for them to travel through the atmosphere and reach the Earth. So they live 2 times 10 to the minus 6 seconds, but the trip should take 2 times 10 to the minus 4 seconds, even if they're traveling close to the speed of light. And the reason they make it down to Earth is that, in fact, in their reference frame, they're traveling so fast, so close to the speed of light, and in their reference frame, time is passing more slowly. And according to the muon, only less than 2 microseconds have elapsed. So this has real practical consequences. Yeah, magnetic force, it's kind of surprising that magnetic forces take you into special relativity, but it's actually what took Einstein into, one of the things that took Einstein into special relativity. All right, we're out of time. So in chat, what was important about today's discussion?
That's for moving with the rotation of the Earth, not via moving reference frame.
We we approximate a reference frame on the surface of the Earth as being not moving. It is indeed not only moving, but accelerating, but it works to treat it as, for a short time, it hasn't moved. So in our we talk about a stationary reference frame as being one attached to the surface of the Earth.
Oh, okay. Because I was just imagining like, so you're at like a fixed point in space watching the Earth rotate. I guess it would be going faster than you, or?
Well, think about how fast it rotates. I mean, you've seen pictures of the Earth from space or movies from space, and in fact, over a short time, the motion isn't very significant. You're right, though. It is an approximation.
Oh. Huh. All right. Have a good day.
Yeah, you too.
Dr. Chabay?
Yeah.
So in the example with Bob and Alice,
yeah,
I know this was just like a hypothetical situation, but like what quantities would they have been they would have been measuring based on like time and then like deducing via math and stuff the other quantities, right?
Right. So what they do is in this example, what they do is they predict how long it's going to take. Okay, because they say, I know the force, I can calculate the electric force here, I can calculate at you know the magnetic force, and so I write a computer program to predict how long it's going to take to get them to hit the floor and the ceiling, and then what they actually measure with their little stopwatches are how long it takes. And so each of them writes a VPython program based on the initial position and the initial velocity to predict how long it's going to take, and then they measure it, and they discover that in their reference frame, their prediction was right.
I guess my brain is just having trouble it makes sense, but at the same time, there's something in my brain wanting to say like, that doesn't make sense. If they're measuring the exact same thing, they should be getting the exact same results, and my brain isn't wanting to comprehend this.
Well, that's right. That's the really interesting idea behind all of this. And this is why Einstein's theory was so revolutionary, because until then, no one could figure out any way out of this problem. The forces really are different. They, you should predict different. You predict different results, and you really do observe different results. But no one had a way to make this coherent until Einstein contributed that. And you might have read about Einstein thinking about riding on a trolley car, looking back at a church clock, and thinking about how if the trolley car went faster and faster and faster, it would take light longer and longer and longer to reach him until if he went almost the speed of light, it would look like the clock never moved. So basically, so he had been thinking about this for a long time, but in fact, it was a brilliant idea, a really revolutionary idea out of this paradox that no one else thought of, and it has been confirmed. I mean, we can in fact, we now have atomic clocks that are so sensitive that if you leave one sitting on a table and pick one up and just carry it across the lab, just walking slowly, you can see the difference in time. I mean, the moving one actually runs more slowly, so it really happens.
That's so weird.
Yeah, it's cool, isn't it? It's one of the one of the cool things.
My brain just keeps thinking like, how do we know that? I'm sure there are answers for it, but I just need to go find them. Like, I need to go like read more about this, but my brain keeps going like, how do we know that like that's actually what's happening, and not like when we move those, like the atomic clocks we're talking about, how do we know that what's happening is not like when we move them, some kind of like the very fact of us moving them is like making something that within the mechanics or something mess up, as opposed to time is going slower?
Well, and those are really good questions, and those are questions that people have worked on a lot over the past century or so, more than a century now. Yeah, so there's a lot of cool stuff to think about and learn about.
Okay, well, thank you very much for staying a few extra minutes to talk to me about that.
No, it's cool. I like talking about this.
All right, have a good day.
Yeah, you too.
Can I ask you something?
Chet, what? Sorry. Yes.
Can you briefly explain the difference between special relativity and general relativity?
Special relativity has to do with effects that you see when things are moving fast or when things are in motion. Okay. So it has to do with time moving more slowly in different in moving reference frames. It has to do with, in fact, it works out that something that's moving really fast actually gets shorter. And you can work that out. So length contraction, whatnot. What general relativity does is it's a much more global thing, and it worries about the effect of large masses on space itself.
So
And the
that's what
idea
black-
behind general relativity is that a very large mass actually deforms space and affects the motion of objects around it that way, and affects the motion of it affects light also. So if this whole gravitational lensing thing, and that time moves slower, it turns out time moves slower near a large mass. And that was actually an effect that turned out to be really important for GPS, that scientists told the engineers who were making the first GPS system that they had to account for the fact that clocks on Earth were actually going to run more slowly than clocks in the satellites for two reasons. One, the satellites are moving, but second, the satellites are farther away from the massive Earth, and therefore the clocks will run more slowly. And I think that the story is the engineers were dubious about that. But in fact, if you don't take that into account, the GPS ends up many kilometers off by the end of the day. Whereas if you take that into account, it's right. So the effect of big masses on time and space is the thing that general relativity deals with.
Okay, thank you.
Yeah.